Hey everyone, welcome back to Calculus 3. This will be part B of lecture 3. And in this we're kind of in the process of moving through some examples of using the dot product and some of the applications of the dot product. So moving on, up to this point, so thinking about vectors in the plane. So for vectors in the plane, let's make sure this is nicely focused. Okay. So for vectors in the plane, we typically measure angles from the positive x-axis to the vector. Okay, that's kind of the convention. Right, that's what we're used to seeing, right? So if I've got my x-axis and my y-axis and my vector v, then what's typical is to measure an angle theta from the positive x-axis up to whatever the vector happens to sweep out. Now in space it's quite different. Okay, the convention is different when we move into 3 dimensions. So in 3D space, all right, in 3D space, the convention is to measure angles between the vector and then the 3 unit vectors. So the convention is to measure the angles between the vector v and the 3 unit vectors. 3 unit vectors I, j, and k. Okay. And so if you've got, this will be your z-axis, and then we'll say this is your y-axis, and then your x-axis. Okay, and if you've got some vector v in here, okay, then the angle swept out by v relative to the z-axis, we typically denote by gamma. The angle swept out by v relative to the y-axis, we typically denote by beta. And then the angle swept out by v relative to the x-axis, we typically denote by alpha. Now this is a terrible picture. It's very hard to see what's going on because it's 3 dimensions. But that's the idea, right? So you've got, you know, in 2D, really there's one angle of interest here. In 3D, the vector can be kind of anywhere situated inside, outside of certain, surfaces. And so really multiple angles have to be called in order to actually triangulate angle-wise. And so we actually have 3 angles of interest for a vector v in 3D space, right? So there's alpha, beta, and gamma, and they correspond to the angle swept out between v and the x, y, z axes, respectively. Okay, so let's just summarize that. So the angle between v and here's where we'll kind of itemize this, I is alpha, v and j is beta, and v and k is gamma. Okay, so these 3 angles here are referred to as the direction angles of v. These are called the direction angles of v. Okay, alpha, beta, and gamma. Okay, and we call the cosine of these 3 angles, so cosine of alpha, cosine of beta, and cosine of gamma. We call these the direction cosines of the vector v. Okay, and this will all kind of come into play here quickly. Okay, and so that's a convention we'll have to get used to. Like, so obviously triangulating things with regard to angles in 3D space is much more involved than it is in 2D space. Okay, but it is still relatively straightforward. You just have to get used to the conventions and kind of get acclimated to them. Do some examples, and you'll see that it's not terribly difficult. Okay, so note, we'll move forward here. Note that if I take v and I dot it with the I vector, well, we saw previously that this is equal to the norm of v times the norm of I times cosine of alpha, right? And I, of course, the norm of I is a unit vector, so the norm is 1, and so this is always equal to the norm of v times cosine of alpha. Okay, so we have that. We saw that previously, and notice, right, also that v dot I is equal to, well, this is just kind of v1, v2, v3 dotted against what, 1, 0, 0. Okay, so it's just v1, isn't it? Okay, so given these two facts, right, so from this it follows, you may be able to see it already, that cosine, well, let's write it out, let's derive it. So you've got v, the norm of v times cosine of alpha, right over here, that's equal to v dot I, and v dot I is also equal to v1, right, so this is equal to v1, right, and that's a scalar, remember, that's not a vector, that's the first component of v. And so this means what? Well, it means that the direction cosine cos alpha is equal to just v1 divided by the norm of v. Okay. Very nice, right? This is a really relatively simple thing to derive, right? This one we talked about last in part A lecture, and then this part here, this is something we talked about two lectures ago, I believe. Right, and then just a little bit of algebra with those two pieces gets us this. Okay, and so we can do this with the first component of v and the direction cosine alepha. We can do it also with the others as well, can't we? Okay, so we can do it with the other direction cosines as well, and so we have cosine of alpha is equal to v1 over the norm of v. We also have that the cosine of beta will be v2 over the norm of v, and also that cosine of gamma will be v3 over the norm of v. Okay. All right, and so from this, it follows then that any non-zero vector v in space has the normalization form so v over the norm of v is equal to v1 over the norm of v times the I vector plus v2 over the norm of v times the j vector plus v3 over the norm of v times the k vector. Right, and another way to say this, of course, is that this is just cos alpha I plus cos beta j plus cos gamma k. All right. Okay, and of course, now this is a beautiful piece of it, right? Kind of taking this, because we know that v divided by its norm is a unit vector. It follows that this is going to be a unit vector, right? Which means when we square this whole thing, take the square root, we get the following: cos squared alpha plus cos squared beta plus cos squared gamma equals 1. And that's nice, right? Because that is, you can think of that as kind of an extension into 3D space of the Pythagorean identity. Not exactly the same thing, but it's very, very much rhymes. Okay. All right. Excellent. Let's do an example. Let's kind of pull some of these together in an actual example with some actual numbers here. Okay. All right, so let's find the direction cosines right, and angles for the vector v equals 2i plus 3j plus 4k. And let's show that cos squared alpha plus cos squared beta plus cos squared gamma equals 1, right, for this particular vector and its direction cosines. Okay, so first thing we're going to need is the norm of v. Right, the norm of v is, it's going to be equal to basically 2 squared plus 3 squared plus 4 squared. Take that square root, and this will be 4 plus 9 plus 16, and so we get the square root of 29. Okay, so then the direction cosines are just going to be, so we'll do the first one, cosine of alpha will equal v1 over the norm of v, okay, which is 2 over the square root of 29. Okay, let's write cos beta. That's v2 over the norm of v, which is 3 over the square root of 29. And then cosine of gamma is v3 over the square root of v, which is 4 over the square root of 29. Right? And so each of these we can use to find alpha, beta, gamma. Right? So alpha will be the inverse cosine of 2 over the square root of 29. Beta is the inverse cos of 3 over the square root of 29, and gamma can be found using the inverse cos of 4 over the square root of 29, right? And so in each case, you can pull out a calculator and plug these in, and they're straightforward, but you get something like 68 degrees and then 56 degrees. I did this at advanced in advance here, and this would be 42 degrees. Okay, so that part's pretty straightforward. Just kind of follow the recipe for these guys. Okay, and so this tells you, what does this tell you? Well, this tells you that the angle formed by v between the x-axis and the angle and the vector v is 68 degrees. The angle formed by v and the y-axis is 56 degrees, and the angle between the z-axis is 42 degrees. Right, so you know exactly where this vector lies in space relative to the three axes, right? Because you have these three angles now. Okay. All right. What about the second piece of this example, where we're asked to identify or to show that we're asked to show that cos squared alpha plus cos squared beta plus cos squared gamma is 1. Well, we can easily do this, right? So cos squared alpha plus cos squared beta plus cos squared gamma. Well, cos squared alpha we saw was 2 over the square root of 29. And then we got to square it. Cos squared beta was 3 over the square root of 29. Yeah, square that. And then cos gamma was 4 over the square root of 29. We could square that. And we get 4 over 29 plus 9 over 29 plus 16 over 29. And of course, that's equal to 29 over 29, which is 1. Okay, so really straightforward to see that. Okay. All right. Okay, and so all of this stuff will come into play once we get a little further into the course, and we start talking, even in the coming lectures, when we start talking about planes and lines and space and how they intersect, and then ultimately surfaces. And then when we start doing actual calculus, these are the tools we'll be using. Okay. All right, let's move on to another definition here. Okay. Let's talk about another definition. This is going to be the projections of vectors. Okay, so let's let U and V be non-zero vectors. Okay. Let's let U equal W1, right, a vector, plus W2, another vector. Okay, where now here these W1 and W2s have properties relative to V. So W1 we'll say is parallel to V, and W2 is orthogonal to V, or perpendicular, whichever term you like. Okay, so you got one that has the same slope and one that has a perpendicular slope. Okay. All right, and so these two vectors, W1 and W2, have a name. So W1, the one that's parallel to V, is called the projection of U onto V, or the vector component. It's also called this vector component of U along V. Okay, right? It is denoted, okay, it's denoted by W1 equals, and then just literally the word proj. It's the projection of U onto V. Kind of some ungainly notation there, but right. So, and there's a second part too, but let's make sure we follow this one. So let U and V be non-zero vectors, and so V is just any vector, but U is a special vector where it's equal to W1 plus W2, where W1 is parallel to V and W2 is orthogonal to V. W1 is called the projection of U onto V. It is denoted by W1 equals projection of U onto V. Okay, so that's special notation there. Okay, now what's the second piece of this? Okay, so the second part says that W2 is equal to U minus W1 naturally, right? Just because U is equal to W1 plus W2, so it's just algebra there, and is called the vector component of U orthogonal to V. Okay, right, so this is all very cryptic. So let's just draw a picture here and see if we can figure this out. What is this talking about? Okay, so we'll do this in 2D space. Okay, so I've got some vector u. Okay, this is my u. Okay, and so let's have this come out a little bit more here. And so then I've got some other vector here, v. Okay, so it's kind of this shorter vector. Now you can kind of think of this as being dropped down, right? And so then this part here, there's another vector that's formed, and that's the vector w1, right? So u is kind of dropped down onto, onto v, right? It's dropped down onto the axis created by v, but it's like of a different length, and that's w1, right? So it's parallel to v. And then over here you've got this other one that kind of comes up like this, and that's w2, which is orthogonal to v, right? So this guy down here, this w1, is called the projection of u, right? So it projects u onto v, okay? And that's the one with the notation here, w1 equals projection of u onto v. And then w2 is just equal to whatever u is minus w1, right, naturally. Right? So if you were to take u and you subtract off w1, that would be, you to put this thing here and it'd be minus, so it would come back, wouldn't it? And so that would give you the vector w2, and it's just called the vector component of u orthogonal to v, right? So you get these two pieces. Okay, now this is for a theta here, of course. I should have put that in there to start with, right? So you've got some angle theta. And this is the case where theta is acute. Right, so when theta is acute, this is kind of what the picture looks like. What happens when theta is an obtuse angle? Well, it's pretty much the same idea, just extends into the other direction, right? So let's say instead I've got my u up like this, right? And so this is gonna, you can think of it as coming down like this, right? And so my w1 is over here, right? And my v is still this direction, right? So this is still my v. Right, but now my w1 is like this. Okay, and then where's my w2? Well, it's right here, right? So you can think of this as dropping back like so. Right, now is it still true that w2 is equal to u minus w1? Yep, right, w1 is here, right? So if I take the tail of w1 and I put it up here and I reverse the direction, I get back to w2, don't I? Okay. Now notice w1 is is the projection of u onto v, right? See what it says here, projection of u onto v, or it's also said the vector component of u along v. It doesn't mean that are going in the same direction, right? These are just two parallel vectors. Okay, they're not necessarily in the same direction. Okay. All right, so these pictures are important, and this is for theta is an obtuse angle, right? The angle between v and u is greater than 90 degrees. All right, very good. So this is kind of a tricky concept. It'll frequently come up and be used to kind of help us calculate things. I think, the raw definition can feel a little bit tricky and weird, but usually when it comes up in applications, it's more straightforward. Excuse me. Okay. All right, let's move on. Let's see if we can toss this into an application and or an example and start talking about it. Okay, so let's remember here that w1 is a vector, and it's equal to, this is the projection vector, the projection of u onto v. Okay, and that's what we would say. We'd say the projection of u onto v. Okay, so v and u are not the same. There's some angle between them, but it's possible to project u down onto v, and that's the vector we call w1. And then w2, right, this is the vector component of u orthogonal to v. Okay, so those are kind of the two pieces. Let's do an example using these. Pull these in here. So let's find the vector component of u equal to 7, 4 that is orthogonal to v equals 2, 3. Given that W1 equals the projection of u onto v, and that's equal to the vector 4, 6, and u is equal to 7, 4, which is equal to W1 plus W2, right? So this is kind of a contrived example, just to make sure we have this one connection sorted out. Okay, so, well, because u is equal to W1 plus W2, right? That's the setup. Where W1 is, parallel to V. So where W1 is parallel to V, right? Keep the picture in mind from the previous page. So it follows that, W2 is just the vector component of U orthogonal to V, right? So basically you can do the subtraction. So because of this, W2 is the vector that is the orthogonal component. Okay, it's the orthogonal component, and in fact, U, so W2 would be equal to basically just U minus W1, right? All right, so we're given both of these vectors, so it's 7, 4 minus, I think W1 is 4, 6, right? So this is just basically a subtraction problem. So that's just going to be 3, negative 2. Okay, so W2 poses no problem. It's easy to find W2 once you've found W1, right? Once you figure out what the projection of U onto V is. All right, so how do we do that? So it's easy to find W2 if we have W1, which is the projection of U onto V. How to find W1? Okay, how do we find W1? How do we get that one? Okay, well, the good news is there is a nice little theorem. Okay, we can always use this theorem. It always works. So if U and V are non-zero vectors, and they're non-zero vectors, then the projection of U onto V is given by, okay, right, so here's that notation, projection of U onto V. It's equal to, well, you take U dot V, you divide it by the norm of V squared, right? That's a scalar. You multiply that by V, right? So remember, we're projecting onto V, so we need something that's in the same direction as V, but it just needs to be longer or shorter, right? So just remember what that picture looked like. I don't know if I can find it. On the other side here. Let's remember what the picture looked like. Right. Our W1 is the same direction as V. It's just longer or shorter depending on what U happens to be. Right. So you could think of it as just we just need to figure out how to scale W1 so that it's really truly represents the projection of U. Right? So that's what we're doing here. That's what this is about, right? So this is the way to compose the scalar, to come up with the scalar, multiply it times V to kind of shrink it or extend it. Okay. All right. So that's how you would find, this is your W1. That's how you figure out what that W1 needs to be. Okay, so notice that the projection of U onto V can be written as a scalar multiple of a unit vector in the direction of V. Can be written as a scalar multiple of a unit vector in the direction of V. Right? So that should be common sense, right? So any unit vector, it's just a scalar multiple of a unit vector in the direction of V. Okay. So what does that produce? Well, so you've got your U dot V divided by the norm of V squared times V. Okay, so that's the theorem we just looked at. And so we would say that's equal to U dot V over the norm of V. Okay. Okay, and then you can take one of those out instead of norm of V squared. Just have one of them there. Right, there you go. And so that's equal to K times V over the norm of V. Right, so that's kind of what we were just describing, right? So here's this constant K times this unit vector in the direction of V. All right. And so K here is U dot V divided by the norm of V, okay, which we saw previously is just the norm of U times cosine of theta. Okay, the scalar K is called the component of U in the direction of V. Okay, so let's flip pages here and recap this. All right, so U dot V over the norm of V squared times the vector V. All right, that is U dot V over the norm of V, right, times V over the norm of V. Right, so this is a unit vector. This is the scalar K. Okay, and so K is U dot V over the norm of V, right? That's what we see right above here. And we know that's equal to the norm of U times cosine of theta. Okay, and what we say here is that K is called the component of U in the direction of V. Okay, and that's what that scalar is called. It's called the component of U in the direction of V. Let's do an example. Let's see how this works out in an example. Sometimes it's easier to see these things when you have actual numbers. So let's find the projection of U onto V and the vector component of U vector component of U that's orthogonal to V. For the vectors, two vectors. Okay, so we've got two vectors. We'll say we've got U which we'll write as 3i minus 5j plus 2k, and v, where v is 7i plus j minus 2k. Okay? All right, so we've got these two vectors. We want to find the projection of u onto v. We also want to find the vector component of u orthogonal to v, right? So we need w1 and we want w2. Okay, so let's figure out how to, so w1 comes first if we're not told what it is. That's the projection of u down onto v. Right, we just saw how to do that. That's going to be u dot v over the norm of v squared. That's going to be some scalar, and we want to multiply that scalar multiplication with the vector v. Okay, so in the case of this is going to be u dot v, so it'll be 7 times 3 is 21, plus negative 5 times 1 is negative 5, and then plus negative 4. Okay, and what's the norm of v? Well, that's going to be 49 plus 1 plus 4, square root of that. And then that scalar needs to be multiplied. This is the scalar multiplication with v. Okay, so let's add all this up. We get, what do we get here? We get 12 in the top. And then this will be the square root of 54. Oh, but that's squared. Let's not forget that. Sorry. And then that needs to be multiplied with v. And so it's really 12 over 54 times v. So 12 over 54 times the vector v is 7, 1, negative 2. So you can write it in whatever notation you want. If you want to use this notation or the IJK notation, that's fine. But just kind of multiplying this through, you get 84 over 54, and then you get 12 over 54, and then you get negative 24 over 54. Okay, and this will all simplify down, and I'm going to put it back in IJK. So this would be 14 over 9 when we do that division. We simplify that first fraction, and then this will be 2 over 9, and then minus 4 over 9. Okay, all right, so this is W1. Okay, not the prettiest vector in the world, but it is indeed a projection of the given vector u onto v. Okay, so it's going to have the appropriate length, and it's going to be in the direction of v. Okay, and then the orthogonal complement, or sorry, the orthogonal component is w2 equals, how do we find it? Take u minus w1. Right, so this is 3, comma, negative 5, comma 2, minus 14 over 9, comma 2 over 9, comma negative 4 over 9. Okay, so you got those two vectors. And we can subtract that. Now it's not as, it's not a terrible bit of subtraction, but you would end up with 13 over 9, right? 3 minus 14 ninths is 13 over 9. And then it would be negative 5 minus 2 ninths, and you would end up with negative 47 over 9. And then 2 minus 4 ninths is 22 over 9. Okay, and so W2 is equal to 13 over 9 times the I vector minus 47 over 9 times the j vector plus 22 over 9 times the k vector. Okay, and so there's your W2. Okay, so you've got both pieces. Okay. All right. So very good. That is the that is the last example for this section. And so that's the dot product. Like, there's a lot of stuff going on there. I realize, right? I'm kind of dumping out a lot of ideas, but all of this stuff will be used going forward. We'll use it a fair amount. So that'll do it for this section. The next section we'll get into what's called another operation between two vectors in space, and that's going to be what's called the cross product, right? So it's a different kind of product. So we've seen the scalar product, we've seen the dot product, scalar multiplication, the dot product, and now we'll talk about the cross product next. All right, very good, and we'll end it there, and we'll talk to you all in the next one. Take care.